you will tell us about CHY and the Collinear limit.
Yes, thank you. I would also like to start my presentation with thanks to organizers for inviting me to present this work and also for a great workshop. We couldn't let Germany win yesterday, but that was not our fault. So still, I'm happy to be here and present some work I did in collaboration with Ritiman Nandan, who's a postdoc in Berlin, and Vadim Wormsmecher, who's my PhD. So the setting is the following. In the past 2 years or so, there has been a renewed interest in soft limits and uncovering of so-called subleading soft theorems for gluons and gravitons, and we heard some talks related to that also in this meeting. These developments led us to address a question which is somewhat obvious after one has seen these subleading soft theorems, namely whether there are similar statements one can make about a universal factorization for subleading collinear limits of gluons. And that has been a topic of our research in Berlin for the last half year or so, and I would like to report on the results we have. So I'll start out with a brief review of the structure of soft theorems, and then turn to the collinear limits and quote some results of Steiner and Taylor, which suggest that there might be a connection to actually Einstein-Young-Mills amplitudes when we look at subleading limits of Young-Mills amplitudes. And that's why we will discuss this in the setting of the CHY formalism, because that presents a unified description of gluon and graviton amplitudes. And we will arrive at formulas which we can also generalize then for gravitons and scalars, and even take thereafter a soft limit after the collinear limit to get some results. So let me begin with the soft theorems, as I said. They date back to the early days of quantum field theory and state that there's a universal factorization when you take a single leg, be it a photon, a gluon, or a graviton, soft, namely the situation where you take the momenta associated with that leg to zero with a scaling parameter which I call delta here. And in such a limit, one has factorization, so the n+1 particle amplitude becomes an n particle amplitude, and there's a certain soft factor or soft pole up front, because it scales like 1 over delta, a scaling parameter, and in the photon, or if you use color-ordered formalism, the gluon case, you have this structure, and the graviton case, you have that structure. The proof of this is elementary. It essentially follows also from considerations of gauge symmetry, and there are, of course, then also loop corrections to this, which have been well understood and studied. Now, the novel results, at least partially in the graviton case, were that this factorization extends to subleading orders. So if I go deeper in the delta expansion of such a soft limit, one recovers so-called soft theorems, which are, as a matter of fact, operators, because they include derivatives with respect to the hard momenta and hard polarizations. So if you look at the structure, we have next to the leading low and Weinberg poles, you have a subleading order that's delta to the naught. These differential operators spelled out here, which contain the angular momentum operator upstairs, and for the gravity you have this structure here where we write the polarization tensor for gravitons and product of TVs in this structure. And for gravitation, it actually extends one order further, so we also have an order delta term, which then takes up two derivatives, or second order differential operator, building upon the angular momentum operator squared. And there is a very fascinating connection to a hidden EMS symmetry, which I do not want to dwell on, but that has been motivation for much of the work. So given these nice structures, a question one might want to ask is what happens in the collinear limit? So, of course, also the collinear limit is a well-studied situation where we now look at a situation that we take two massless legs to be collinear, and one then again observes factorization to a lower point amplitude pressed up with a splitting function. And what we want to ask now is a question if there is whether there is a subleading structure here as well, and for this we have to parameterize this collinear limit, and a very convenient way of doing that is the one spelled out here. So in our situation we want to take the leg 1 and 2 collinear. We control this so they're collinear to a momentum p, and we control this by an arbitrary angle, phi, and abbreviate the cosine and the sine is with a c and an s. And r is now a reference momentum, which is different from p, in order to parameterize the getting closer of leg 1 and 2. So this is the parameterization we use. We control it by epsilon, so if we set epsilon to 0, we have a collinear situation, and the level of spinellicity variables is this here, but I can also write it dimension independent in this fashion here with parameterization in this version. So you see that, in fact, in this way of doing it, total momentum is conserved up to order epsilon squared. So P1 plus P2 is violating, is not equal to P up to order epsilon squared, which we should keep it. Okay, so armed with this, the question now is whether we could have a universal factorization of gluon amplitudes at a subleading order in epsilon. So at leading order in epsilon, as I said, at tree level, the situation is well understood. So if I take two gluons collinear, I have 1 over epsilon pole, depending on the polarizations. These are the splitting functions that pop out. So they depend on S and C, and of course on P and the reference group. Right. So the question for this talk is whether there is also a universal factorization at subleading order in epsilon. Of course, we do not have any potential hidden symmetry at the horizon for such a thing to exist, but still we can just go ahead and look at it. The first thing one might think of doing is to look at BCFW description of the problem, because there it is rather straightforward to extract the tree-level splitting function, so the leading order behavior. So if I look at a situation, again, 1 and 2 are the collinear legs, and I do a 1n shift, then one sees by looking at the constituting diagrams in the BCFW expansion that the leading contribution, so the splitting function, comes from a situation where we have a 3-point vertex on one side and on the other side and an n-2-point vertex. And that then the parameter z scales like epsilon squared. So you find the order 1 over epsilon contribution exclusively from this class of diagrams, and that of course is a signal of factorization and universality, because it doesn't matter what the other legs do. If you look at a generic diagram, you quickly realize that these scale as order 1, and that indicates that at subleading order you do not expect a factorization anymore, because this is spreading, the contributions to the subleading order speak to all legs. However, one drawback of that argument is that you are only looking at linear combinations of gluon amplitudes. And this work I mentioned at the beginning by Stieberg and Taylor alludes that there might be a connection to Einstein in those amplitudes. So let me review this. So what Stieberg and Taylor did published last summer were quite intriguing relations between Einstein-Yang-Mills amplitudes and pure Yang-Mills amplitudes, and Stefan also reviewed some of this in his talk yesterday. So explicitly I spelled out these relations for lower multiplicities, 10, 5, 6, and 7. So the red amplitudes on the right-hand side here are always Einstein amplitudes with a single graviton and n-1 gluons. And there are relations between these amplitudes, and particularly linear combinations of the n+2 point gluon amplitudes, which, as a matter of fact, when you take a collinear limit of 1 and 2 in all these cases, have vanishing. So the linear combination is exactly such that the splitting functions, the leading order contributions, cancel. So the subleading order contributions of these linear combinations are given by Einstein-Mills amplitudes. However, the set of identities that were derived by Stieber and Taylor only half as many identities as you would need in order to completely fix the subleading structure. Because at tree level we have n-3 factorial independent tree-level amplitudes. If we want to understand their subleading collinear behavior, we would need as many such relations. However, these results only give you n-3 factorial over 2 constraints for these subleading classes. So that's why it's only half the solution, and one would have to search for the second half in order to rewrite all the subleading collinear gluon amplitudes as some combination of Einstein-Mills amplitudes, or whatever could be on the right-hand side. So in any case, so these results suggest, or may let you hope, that there could be a relation, as I boxed down here, namely, that if I look at the subleading collinear limit of 1 and 2 of an n-gluon amplitude, I could write it as some subleading collinear operator S1 acting on an Einstein-Mills. Okay, so given this relation and the problems or the negative results which one extracted from BCFW is not necessarily a contradiction, because BCFW would only do recursions in the space of gluon amplitudes, whereas we have to enlarge our amplitude space, or the helicities of the participating particles, also to the graviton case. And for this question, it is rather obvious that the Cachasso-P-UR formalism is the right thing to go, because that provides you a very unified description of all graviton and Mills amplitudes. So this is what we want to address, namely we want to now study the collinear limit in the CHY formalism. It turns out that just even extracting just the splitting function, so the leading collinear behavior in CHY, had not been performed so far, so this alone is also of interest. So let me give you a brief review of the CHY formulation. So it is based on these famous set of scattering equations, which are spelled out here. The sigma A are exactly n complex parameters over which we integrate in order in this CHY representation of the amplitudes. And these scattering equations have exactly n-3 factorial solutions, which incidentally is the same number of independent tree-level amplitudes. However, there's no clear connection why that is. So, in any case, the unified description is now such that we integrate over the sigmas, dividing out an SL2C symmetry factor, and putting all the sigma intervals on the solutions of the scattering equation. So in principle, this is nothing but the sum over all solutions of scattering equations, where you plug in the particular solutions of these sigma A's in the integrand In. Now the integrand is built from fixed building blocks, which are of two kinds here. One are the so-called Park-Taylor factors, which is this combination of a product over sigma ij's, where these are always the differences, and then this famous n plus 2n cross 2n CHY matrix psi, which is antisymmetric. It has entries in these four blocks here. In the n block A, these are essentially the densities of these scattering equations. And we have in the B block the product of polarizations, and here we have polarization times momentum-like terms. And in fact, whatever combination you take now of C and psi, you can write down various massless bosonic amplitudes in any dimensions in a very unified fashion. So again, this is the CHY formula. If we just take gravitons, we take we compute the Pfaffian, so the square root of the determinant of this psi matrix, and square it. If we take gluons in a color-ordered fashion, we take Park-Taylor factor and this Pfaffian. And if we take mixed situations, in particular the ones we want to be looking at, where we say we take one graviton and n gluons, you would have, for the gluons you have the Park-Taylor factor, then you have one CPP, which is essentially the entry of the C matrix here, just for one particle. So it's exactly this, the diagonal piece, it's this expression. And you also have an n plus one particle Pfaffian. And you see that just looking at the polarization tensors, so you have n plus one polarization tensors here, and the p1 is doubled, so that's exactly what you need in order to describe the polarizations of the graviton at position p. So here you have a very unified description of gluon and graviton trees. In fact, you can also just take two Park-Taylor factors, and then you would describe the phi-cubed scalar field. Okay, so in this setup, we now jump in and look at the collinear configurations. So we want to take this near collinear limit parameterized by epsilon. Now, the question is how can we address that? And it turns out that it is very convenient to make the following change of variables from the two sigma coordinates which are affected by this collinear limit, sigma 1 and sigma 2, to rho and psi, the sum and the difference, because you in this parameterization you can see that degenerate solutions for sigma 1 and sigma 2, so if the solution of sigma 1 and sigma 2 the points coincide, that these imply collinearity of the momentum P1 and P2. This you can see if you just make an ansatz for psi1 to scale like epsilon and work things out. So you have this set of scattering equations. So this would be the A are all particles except for 1 and 2, and then I take the sum and the difference. And you see that these just build up to a set of scattering equations for the particles with one reduced, with one less, and where I put in the momentum p, and the difference is then singular in epsilon and proportional to p1 dot p2. So in order for this to vanish, that enforces the collinearity of p1 and p2. So the statement is that degenerate solutions for sigma 1 and sigma 2 imply collinearity. The question then is whether the opposite is also true. That's what I said. So if sigma 1 approaches sigma 2, necessarily the momentum p1 and p2 have to be parallel. But is the opposite also true that for p1 and p2 parallel, all sigma 1 and sigma 2 solutions fall together? Remember that there are n-3 factorial solutions in the problem. And in order to answer this question, this is not so easy. We embarked on some numerical analysis. So we looked at configurations up to 8 particles with near collinear P1 and P2, which we parameterize with a small parameter epsilon. And for this, it is very useful to use alternative formulations of these scattering equations. In particular, we use the ones due to these authors here. And what we found in these numerical experiments, that there are always, in all these cases we looked at, 2 times n minus 4 factorial degenerate solutions. So solutions where sigma 1 and sigma 2 fall together, or where psi 1 goes to 0. But there's a remaining set of n minus 5 times n minus 4 factorial solutions where they are non-degenerate. However, if you then look at their contributions to the CHY integral, it turns out that the non-degenerate solutions do not contribute at the leading, and at least that's what the numerics suggest, also not at the subleading order. So that's interesting. So that means that we should focus on these degenerate solutions in order to understand the behavior. Okay, so how does that now go? In the scattering equation, we focus in on the F1 and F2 equation, which we now rewrite as the sum and the difference, as the parameterization in rho and psi suggests. And we make this scaling ansatz that of a degenerate solution, psi1, as an order epsilon term, and then higher terms. And then, to be consistent, one actually has to consider this particular linear combination here, which I call F minus, which is then a pure order epsilon term, as F plus, which is F1 plus F2, starts out at order 1 and then at order epsilon terms. And then I can solve for psi1, and I find two solutions for psi1. It's a quadratic equation, which is somewhat involved and spelled out here. And that's nice because that exactly reproduces our numeric analysis, namely we find two solutions for psi1, which are degenerate, and we still have a set of n minus 1 generic scattering equations for the generic momentum, which have n minus 4 factorial solutions. Therefore, I find 2 times n minus 4 factorial solutions, which is exactly the number we also found from numerics. So we're quite confident that we have found all the degenerate solutions in this approach. Okay, and then now the rest is just straightforward, yet tedious, so we have to insert these solutions in the integrand and sum over them, and assemble all the terms at the various orders in epsilon. So there are 4 contributions in this near-collinear expansion which we have to look at. So as I said, we perform the psi integral. That's like we found the solution, so that we perform the psi integral, but we leave the rho integral and all the n minus 1 remaining sigma A integrals inert, because we want to rewrite this as an n plus 1 particle amplitude. So when there are 4 sources of epsilon corrections, of course from the Park-Taylor factor, from the Pfaffian, then we get a Jacobian by doing this F1 minus F2 integral, F1 minus F2, delta functions, so we get the derivative of it with respect to psi, always psi plugging in the solution and then summing over the solution. And then we also have to watch out that there is an order epsilon correction to the FP delta function, which will also contribute at subleading order with the derivative on the delta function. So that's quite peculiar. So the Jacobian has a leading order 1 contribution, and the Park-Taylor factor turns out to scale like 1 over epsilon, whereas the CHY matrix scales like 1, like epsilon to the 0. So just by looking at the scaling, we can immediately see what the collinear behavior is of the various particles that we can describe with CHY. So if we look at gluons, we would pick a Park-Taylor, 1 Park-Taylor factor and 1 Pfaffian. So that means gluons have to be singular in the collinear limit and scale like 1 over epsilon, which is exactly what we know from the splitting functions. Gravitons do not have a Park-Taylor factor, so they will not be singular in the collinear limit. They will scale like epsilon to the 0. And if you want to look also at scalar theories, you get a 1 over epsilon squared term, so you have a very highly singular collinear behavior. Of course, this is all known, but it's just reproduced by these scalings. So, clearly the complicated thing now is to work out this Pfaffian expansion epsilon. The rest is rather straightforward and already on the slides. So, for that, we essentially go back to our linear algebra graphes and remember the elementary matrix manipulations that we can do, which will not alter the determinant. And so here, just to show you the complexity, I spelled out this matrix where I singled out leg 1 and 2. These are the 2 hot legs, the 2 linear legs. And in order to compute the Pfaffian, you just pick a row that expand around that row. So we want to focus at row 1. And there now is a particular set of elementary matrix manipulations that you can do, which will just place as many, which will put as many zeros as you can assemble in row number 1. This is what I spell out here. So you add row and column 1 to 2, and then subtract c squared times the second row from the first row, and the same for the columns. After doing that, you manage to put all the epsilon terms in all entries except for these two here. And that's what I sort of color coded with the epsilon term. And then there's an interesting B1, 2, which whose form depends now on the helicities of these gluons. So if they have the same helicities, you get a 0, and if they have opposite helicities, you get a 1 over epsilon rho. So the same helicity situation is much simpler because you put a 0 here, and then at leading order you would just have to look at the expansion of these two rows, which are as a matter of fact identical. However, if you look at the mixed helicity case, and you have to also include cross terms. In any case, once you go through this rather tedious expansion, you get your results. So let's look at the leading order. First, when we have same helicities, so then the Pfaffian expands as follows. You get a Pfaffian, an n plus 1 point to the particle Pfaffian as you expected, and these particular combination of terms, depending on whether you have plus or minus helicity. So if you now stick everything together, this is the result you have. So you sum over the solutions. This comes from the Jacobian, from the Park-Taylor factor, this from the Pfaffian matrix expansion. And indeed, after using identities like, you have to still sum over these solutions. So as a matter of fact, the leading contribution from the Jacobian divided by psi1 summed over the two psi1 solutions is 0, whereas when you sum over psi1 squared, you get this factor. So that actually completely kills this guy, and only this one contributes, and you assemble everything to the splitting function. So this was a long way to reproduce something already known. And you can do the same game for the opposite helicity case. Now you get two contributions which yield the two splitting functions which contribute when you have opposite helicities on the two collinear gluons. So the tree-level splitting functions are recovered from CHY, but this was of course just a warm-up because now we have everything in place to go down to the subleading collinear limit. Now, the final result, after a lot of sweat that you get, by combining all the subleading contributions from the Jacobian, from the Park-Taylor factor, from the CHY matrix, and also from the derivative of the delta function, spelled out on here. And the fact that you get a derivative of a delta function of fp tells you that you should be able to rewrite everything as a total derivative with respect to rho. So these are the purple terms down here, which we can throw away. And what remains is a structure which does talk to Einstein-Yang-Mills amplitudes, because we have an n plus 1 particle Park-Taylor and Pfaffian structure, and we have the CPP, which was the entry that we had when we wanted to describe n plus 1 point graviton gluon amplitudes. But there is this other stuff still floating around. So you see there's a particular simplification of this formula when you set C is equal to S, which makes it rather compact. But before I do that, let me show you the result once more, where I dropped the total derivative term. Now, in order to reproduce these Stieberger-Taylor results, we have to perform permutations, sign permutations about over the 4 to n plus 2 legs in a particular fashion. And it turns out that this now manifestly works due to the following property. Maybe under these permutations, only Cn plus 1 and 1 over and sigma n plus 2 comma rho is not invariant. All other entries here are invariant under these permutations. And the key identity is that if you perform this Stieberger-Taylor sum on Cn plus 1, you get P1, where P1 is this particular contribution here, and it's nothing else than the carrying equation for the P particle. So that is 0, and the other term builds up to P2, which is what the doctor ordered, because you have this annoying P2 downstairs, which gets cancelled, and indeed, from this relation you then recover the Stieberger-Taylor result, which I spelled out explicitly here for the 5 pointers. These were the things I showed you at the beginning. So we reproduce what they had, and we have a complete result. However, it's very non-trivial to rewrite this as an operator acting on this n+1 amplitude, essentially because we have a P2 downstate. I said a simplification comes when you look at the democratic collinear limit, where you distribute the p momenta evenly over leg 1 and 2, because then these cross terms go away, and then you have a very nicely looking formula, which is this one here, and just P2 just as a comment, it's just a derivative with respect to rho of Fp, which is also sitting in this in the scattering equation, the delta function. So still, although we have been staring at it for a while, we have not been able to write it in a factorized form. So we cannot give an operator, a differential operator, acting on the Einstein-Janodes amplitude, which would produce this stuff here in the integral. So as it stands, we have a closed expression for the subleading collinear limit, and for lower multiplicities you can also evaluate it explicitly, but we do not have a true factorized collinear theorem. Okay, that's a bit disappointing, but that's the result. Of course, we can now use spin-offs and also look at the collinear expansion for the other particles hidden in here. So we can also do the same for gravitons easily now. For gravitons, we start out with the product of two Pfaffians. Now, I'm looking at the n particle situation, and then just inserting all these relations. This is the CHY representation at subleading order. No, actually at leading order. This is order 1. There's no 1 on the epsilon term. And once you perform another integral here, you can recover a result which was already spelled out in this paper in the late 90s as a factorized contribution. And then there's also a non-factorized contribution. And here we can also easily show that it is universal, in the sense that if I change the helicities of the other non-collinear legs, for example, if I take n gravitons and k gluons as a starting point, and then take two gravitons collinear, I recover this structure. This is just the same where I replaced where I inserted an additional number of gluons. Then the next thing one could look at is scalars, and these have to go like 1 over epsilon squared. Again, the leading order is very simple. This you could easily extract from Feynman diagrams. What is interesting is that the subleading order is actually 0. So you get two contributions from the Jacobian and the Park-Taylor factor, which exactly cancel each other. So here we have, if you want, a subleading collinear theorem, which is what you can also do with these results is you can take, after you did the subleading collinear limit, you can now take a soft limit on P. And then, as a matter of fact, you can find a universal factorized expression. So what you have to do is you have to perform the rho integral in order to go down to an n particle amplitude, and this you can do, and what you end up with is this structure. So this is a subleading collinear leading soft result. You first take P1, P2 collinear, look at the subleading structure, order epsilon to the 0, and then send P to 0, which gives you 1 over tau squared. So that's a new result. Okay, so that was what I wanted to tell you. To recapitulate what I was saying, the initiating question was: is there a subleading collinear theorem for gluons? And we were sparked by this, by these interesting relations that Stieberger-Taylor introduced stating that particular linear combinations of collinear, subleading collinear gluon amplitudes are given by Einstein-Wills amplitudes, and we reproduce these findings by analyzing the subleading behavior in the CHY formalism. We can present final formula, but we do not see the factorization because we cannot rewrite it as an operator acting on a lower point amplitude. For gravitons, the leading factorized and non-factorized contributions, the collinear limits were established for these cubic scalar theories. We completely understand the subleading behavior. So it's simply action. That was what I wanted to tell you. Thank you.
Questions for Jan?
So tree-level gluon amplitudes are the same as in planar n equals 4 super Yang mills.
Right.
And there's the flux tube OPE, which, at least in the case of 6 gluons going to 5, is literally the linear and near collinear limit. So that suggests that there is a factorization of the subleading terms. It's just that it factorizes in terms of the flux tube rapidity. And then you have to do a kind of a Fourier transform to get back into momentum space.
Yes, it would be very interesting to look at it from that perspective. I agree. What's not so clear to me is how you can generalize to arbitrary multiplicity.
More questions?
One natural question could be one loop, where you could use this loop scaling equation. Have you looked at that?
I have not yet looked at it. I was a bit disappointed that I did not find a collinear theorem, so it's not clear to me how interesting it would be to go to one loop order. But it would be
So you're using this parameterization regularly in terms of the spinors, but then everything you use is E dimension. So is your result valid for general dimension or for general dimension?
the result is valid for general dimension.
Independently of the fact that you're choosing this parameterization in terms of spinors.
I think that is true, yeah. Would be, yeah.
More questions? If there are no more questions.
I have one myself.
So, in the last case of collinear plus a soft limit, is that equivalent to just a double soft limit of the two ones? Is there a relation?
It's not equivalent because when you take the double soft limit, right? So if I take the collinear limit here, I have a P and a reference vector R. And if I go to the subleading order, I sort of work at first order in R direction. When I take the double soft limit, I'm exact in whatever, Q1, Q2, right? So if I take double soft and then only take the first correct, so that, rephrase Q1, Q2 in terms of P and R, then double soft has more information than collinear, subleading collinear and software. Part of the terms agree, but there's more information in those.
More questions? Going once, going twice. There are no more questions. Let's thank you again.